Hello to everyone. My name is Artem, and today I would like to share my progress, the progress I've made on my project. And before starting, I would like to say a huge thanks to IRIS-HEP for giving me this amazing opportunity to work on this project with such mentors. And I'm also deeply grateful to my mentors, Jim Pivarsky and Philip James Ilton, for their constant support and dedication, because there was times when we spent nearly an hour working through some errors together. And because of this, I've always felt like we were truly collaborating on this project together. And that support made a real difference. They were always ready to help, and together I believe we have achieved great results. A special thanks to Robert, who, as I recall, has been organizing these meetings for 3 years now. We really appreciate it, so thank you very much. Now about the project itself, as you can see, it's called Array-Oriented Python Interface for the Pythia event generator. And so this sum up its purpose quite well, and let's get started. Let me tell you a little bit about Pythia itself. Pythia is an open source library designed for generating events from particle physics, and it's widely used in particle physics, data analysis, and model testing. While it's written in C++, it also has a Python interface, which we will dive into shortly. Okay, what is the goal and purpose of this project in general? One key aim was to make it easier to install this library in environments like Google Colab, namely Jupyter Notebook. And previously, installing Pythia required installing it from a source file, which was time-consuming. So we focused on creating lightweight, pre-built binary wheels for each platform to make installation faster and simple. So about the main goal, the old version of Pythia had trouble handling large dataset, especially when saving data in NumPy arrays, because when you have arrays, they all should be in the same shape. In case of NumPy, and you need to fill them with some junk events if they are not compatible with desired shape. So it takes a lot of memory. Yep, and how did we solve these issues? First of all, we made Pythia easy to install with just a simple pip install command. And we created a set of wheels for different systems like Mac, Linux, and various Python versions. If I remember correctly, we created wheels for Python starting from 3.8 to 3.12. So it should work fine with those versions. Our second step was to introduce awkward arrays into Pythia. And we need to delve into this one because awkward arrays, it's really cool thing that allow us to create arrays with flexible shapes and contents, which makes them much better than NumPy for this kind of tasks. So when we are dealing with large data set, with large events, with particles, etc. So about awkward. The most important thing is that awkward supports irregular and nested data structures. So it handles variable length subarrays efficiently, ideal for hierarchical or sparse data. When you have different shapes, it's just ideal. Memory efficient, NumPy compatible syntax. It's not so far from NumPy in terms of syntax, so it's not too hard to understand if you know NumPy. Then it supports element-wise operations, custom data types, because in one array you can have strings, floats, integers, etc. It's not a problem. Also, it handles missing data, because if you don't have some kind of data inside your event, you can just replace it with none, and nothing bad happens. Yep. So about the results, achievements. As you can see in this slide, I installed Pythia in Google Colab in Jupyter Notebook, and it took only 9 seconds, which is quite good if we are comparing installing from a source file. Then we reduced the wheel size from 100 megabytes to 25 megabytes approximately. Then we integrated awkward arrays into the next batch function, enabling users to specify the desired number of events and receive them in a lightweight awkward array format. It looks like this. So here is a simple Pythia initialization where we are telling next batch function to generate 3 different events, and it generates awkward structure with 3 events. Here is a detailed example of one of the events, which consists of 57 particles. For each particle, we have such parameters like ID, status, mother1, mother2, daughter, and etc. And here's a close look on one of the particles itself. So you can see that it has ID, status, mother1, mother2. It can have or it vprot parameter, but if it's not specified or not generated, there would be just none, and it's okay with awkward. Yeah, that's basically it about our next steps. We want to test and troubleshoot newly added features and test our next batch function to see if everything is all right. And yeah, I think that's basically it. So thank you very much. If anyone has any questions, I would like to answer.
Thank you, Artem. Any questions for Artem?
Yes, may I ask you a question?
Sure.
So does the wheels which you created are publicly accessible via PyPy repository?
Yeah, you can just pip install and specify the versions that you want. I think now we have .0 and .1 versions, and so you can try and use them.
Thank you. Thank you for answer.
Yeah, the link is in the chat if you want to look, Dmytro, too. So, Matthew?
Hey, thanks for the nice work and the nice talk. So yeah, maybe kind of following up on just the previous question. So the library name or the package name on PyPI is Pythia 8MC, but the library name that you import on that's still Pythia 8. Is that correct? It's okay.
Yeah, it's just my local and local environment, and we didn't push next batch function in newly created functional because we need to test it.
Okay.
But yeah, it's just my thing that it's working locally. So
Sure. And then just a more technical question. So on the previous slide where you note that you've, reduced the size of the wheel by 75%, which is, excellent. Can you maybe just give a few quick words of how you were able to do that? Like what technically was required to still be able to distribute the actual compiled extensions along with all of the PyBind 11 bindings, but with a significantly smaller wheel size?
Yeah, sure. We've done this by removing debug info from our wheels. So we just removed all text information about bugs, about debugging processes like try except, for example, and yeah, and that's it. So now we have this flag that is called, I think, debug, and you can specify it when building wheels. and if you tell the models, for example, debug true, it will generate wheels with debug information,
Okay.
and they would be with the same size, so 100 megabytes, or you can just generate it without it, and it's up to you.
Yeah, so you just basically got rid of all the debug symbols and during. Okay, all right, cool.
Yeah.
And then one final question. So I'm a huge fan of this work, but I was also interested, since you did this work like with Jim and Phil is part of like the Pythia collaboration. Is there a path towards trying to also get these the work that went into making the Python bindings and this in the wheel more efficient, to also being able to get that into the releases that would be able to make their way onto Conda Forge, so that the builds distributed on Conda Forge could also benefit from this technology?
Yeah, we should speak with Phil about it. If it's beneficial, then we maybe do it.
Okay,
if
cool.
we would have time.
Okay, yeah. Thanks very much.
Thank you too for nice questions.
All right. Thank you, Artem. Dmytro, you're up next.
I want to present the project. Project is some kind of proof of concept project. So the project is usage of CUDA to improving SLT performance. I am Belitskyi Dmytro, and my mentor is Andrei Usachov. Well, so what is the prerequisites? Well, as you know, on the large cosmological scale, there is events, there are some observations which don't align with currently existing theory. It's all related to dark matter, and so there's need to fix that. Well, from the point of view of particle physics, we could introduce some novel particles to the standard model to make the theory just describe these events. Well, it's quite tricky to do that. So there's theory which says that, well, could exist some particles in the standard, beyond standard model, which interact solely through gravitational fields. Well, but to register these particles, we make assumption that these particles should decay to the standard model particles via some novel methods. And then we register these particles, standard model particles. They should leave some quite exotic trace in the low-level data, and that's what we are searching for. When I'm talking about the low-level data, I mean the data from the Vela detector in the LHCb. So Vela detector is basically a tube fitted with circle detectors. It have length of 1.5 meters and the wide radius of 4 centimeters. Well, so the primary goal of this detector is to detect vertices. Vertice is basically a point in 3D space which correspond to and basically in this point there occurs some process like decay or something. And so we have these points, okay? And what should we do? So our project, we don't work with real data. We work only with synthetic data. So we generate two samples. One is we generate samples in the program called Gauss. So one sample is represent background noise. Another one is represent background noise with mixed in some anomaly data, which this data was generated according to existing model of these dark particles. Well, so we have two samples, and what should we do further? We will train the neural network, this type of autoencoder, on the background noise sample. Well, and what we hope for, that when we give for this autoencoder to the input data is mixed in anomaly signal, it will struggle to reconstruct this data. So what autoencoder basically do, it's take input and it's compress it and then decompress it. Well, and so if it's not familiar with anomaly or mix it in parts, it will struggle, and measuring but how much it struggle, we could derive some criteria to decide which events we should keep as events with good signal and which is just background noise. Well, so we generate this data, background sample, and background sample with mixed in noise. Then we introduce few cuts, it's geometry. So we just get rid of everything which outside of the detector. We also get rid of data which is how to put it, which is caused by interaction of particle with detector matter. As you can see at the lower right picture, I plot this data in 3D space, and it's quite beautiful. It's not related to this work, but it's quite cool. It represents the silhouette of inner structure of our velo detector. Well, and then also we say that our data should contain more than 3 tracks. So each vertex, it has some parameters, and one of them is number of tracks which go from this point of space. Well, at the upper left picture, the upper right picture, you can see the sample, the final sample, which basically in this shape it was fed in the autoencoder. So the first entry is number of vertices or number of tracks, and the other number is basically the distance from the origin. Origin is a point where proton-proton collision occurs. The number of proton-proton the distance from origin is given in millimeters. Well, okay. So that's how it is, and then basically all this data, it was organized into vector of 12, vector of the length of 12 with float 32 data type. No, so it was introduced some padding and truncation to fit the data into such vector. Here's the plot, so just visual clue how it's all look like. So the num tracks by the x-axis and distance from the region by y-axis. Well, and then all of this was fed into the autoencoder. The encoder will have, it look like 5 layers, fully connected layers with size of 8, 4, and 3. 3, the middle layer represents the latent space, and then decompress the data from this layer back again. Well, and we train it on the CPU because the network quite light, and there's quite a bottleneck to load data from the GPU again to the RAM, and I try to do everything on the PyTorch. I hope it could make things faster, but it wasn't successful, so we decided to left it to train it on the CPU, and so it is. I trained it for the 100 epochs, which with patch size of 512. Well, I forgot to mention that the background sample data contain 8 million entries. And so this is the final result. On the lower left picture, you can see there's a plot of RMS root mean square error. This is just basically the histogram, which error of reconstruction of the some test sample of background noise, as it's supposed to be the sample wasn't taken part in training, and the another sample with this background noise with introduced signal, anomaly signal, and as you can see, they quite differ. And based on this plot, there's one plot to the lower right part, and there is the useful signal in the percent by the y-axis, and the loss threshold, which basically RMS root mean square value, which our encoder gives us. And as we can see from this value, we have to these lines, and actually also SNR signal to noise ratio. And based on this, we could, based on our needs, we could pick some threshold value of RMS loss, based on which we will pick. So how it works? This on the encoder, we feed in vector of 12, receive output, compute the RMS loss, and we see this, let's say, for example, number of 10, and we say that our threshold value is 5. So if it's greater than 5, then we say, okay, this will be our signal. And if it's lower than 5, we say that's okay, it's background noise, we will not use it. And basically, that's it. That's the whole work. It's well, for now, it's just like proof of concept. Well, but there's a lot of work to do further, because I picked the simplest shape as here of data. So it's basically two numbers, but there's more data from the detector available. So what we plan to do is to make the model much complex, and so hope to improve the signal to noise ratio. And that's it.
Thank you, Dmytro. Any questions? No questions? All right. Thank you for the talk. Valerie, you're up next.
I'm going to talk about statistical treatment for analysis grant challenge from IRIS-HEP using RooFit. What was done? So basically, IRIS-HEP analysis grant challenge. This is a big example workflow how analysis can be done. It's done using a lot of different Python tools such as Cabinetry, PyHF, Uproot, Coffee, Awkward. So a lot of different things, and together this is example using Atlas and CMS Open Data, how analysis can be performed. And the goal of this is to provide people already prepared code and show this is how it can be done, and to not to force students work on software, but work more on physics using already prepared software. So before IGC already was partly implemented using root from CERN. So, but it only was taken for data obtaining from root files and then converting this into histograms. Then the final part of analysis, such as configuring templates using some hist factory tool and fitting this template, was not implemented via root. while in reference implementation, it was implemented with cabinetry and PyHF. So goal of this project was to configure template feeding and histogram creation with root. Also, analysis grand challenge proposed to people good visualization, which can be done using one line of code. As you can see, as on the left, for example, it's a results of feeding parameter, and the right, it's like histogramming. This is implementation results, which was done. So the same code which is done via cabinetry and PyHF was implemented using root_cern and root_cern implementation with some additional code, and also was validated for all uncertainties, all parameters up to some floating point uncertainty. So here in the left part of the slide, you can see exact values which was obtained from PyHF and from root hist factory plus RooFit with uncertainty, and right part, this is values for rest parameters, not only parameter of the interest, for PyHF and also for RooFit. So they're almost same. Also, fitted histograms can be drawn now using root, also with extra implementation, but only in the end for user, it's only 2 lines of code. So you can take a look how it looked like and compare also with results which was implemented using PyHF and cabinetry. Then we also added possibility to output correlation matrix and save it to file, since in root_cern it also was done, and we just needed to provide possibility to user easily obtain this correlation matrix. Also for GitHub, we added action sequence. So right now, any changes what possibly could be added to AGC implementation of root are gonna be run with this GitHub action and checked if this change does not affect end state results, such as like fitting results for all parameters, or histograms obtained, or like histograms which obtain it. Right now, final pull request is still open, since we already had some discussions about better way to implement code, about refactor it a bit, make it a bit simpler. I will add a link, so add the link is already here. I will upload the slides, and you also will be able to check this if you're interested how it was done. I will quickly talk about code structure, since I told that it was not done only with RooFit code, but also required some extra tools. So we implemented AGC sample, which introduced some simplification to root hist factory interface, which existed in cabinetry but was not added into root. But these features are not implemented in hist factory yet. There's also rabbining tool, which can be used for rabbining histogram plus bin cutting, since bin cutting are not really exist in root_cern, and we also have drawer, which responsible for graphical output for all plots, which was shown today. And is there anything extra to do? The main part of the project is almost done as soon as PR would be approved, but there is still some room for improvements inside root_cern repository. So part of code which just was discussed still could be migrated to root_cern, and such migration would not only simplify the root AGC repository, but also make the analysis tools available for people like outside of AGC. And this is some next steps which I'm gonna do next. So now AGC CMS TT bar analysis fully implemented using root CERN from the beginning up to the end. These tools can be used for any analysis. User interface is simple and easy to use. This also was one of the goals for this project, and further developments for root repository are also expected in future. Yeah, so that's all about my work during this fellowship. I would be happy to answer any of your questions if you have something.
Any questions for?
No question. I just have a comment. Thank you so much for this great work. This is one of these pieces of work that I think will have an impact for months to come. Because I mean, sorry we didn't have the time to merge your PR yet, but this will for sure inspire lots of improvements in the root interfaces, both in RooFit and also in the visualization part.
Thanks a lot.
Okay. One logistical thing, Valerie, send me your slides when you have a chance, please, so I can upload them.
Yeah, of course, I will send it via Slack. Sorry, I really forgot about it.
No worries, but thanks. Okay. Up next is supposed to be Maxim, but I don't think Maxim's connected. Yurii, you want to go ahead and share your slides?
Yeah, you can. Okay, I'm sharing the screen. Can you see it?
Yep.
Okay, hello everyone. My name is Yurii Perets. I am KU National University student. I'm working on the project CI/CD improvements for Alpaka library and related projects. My mentors is Valerii Kholoimov and Yurii Perets. So first of all, we need to start. What is it? What is it Alpaka? Where did it came from? So our modern experiments and experiment of next generations like Dune or High Luminosity Large Hadron Collider, both of them is gathering a lot of data, and especially need more computational powers to somehow compute this data. So for this analysis, high performance centers, for optimizing this problem, they usually use heterogeneous computing. It's the case when you use not just simply CPUs or GPUs but you use both of them simultaneously. So in this case, you have one problem that most people are familiar with the CPUs programming. But GPUs programming is very different from CPUs. And another problem is that GPUs programming is different from itself. Like you can use different libraries, and it may have different syntaxes or something similar. So in order to update facilities, in order to use new computational accelerator power, you need to rewrite a large amount of code, and it is inefficient and it can be expensive. So in this case, we use Alpaka. Alpaka library defines and implements an abstract interface for the hierarchical redundant parallelism model. So what does it refers to? Hierarchical parallelism model is the technology that was used by the CUDA and OpenCL in 2007 year. It refers to, roughly speaking, we divide our GPU's powers for groups, then by subgroups, then by subgroups, like in this case. But in the case of Alpaka, why it redundant? Because we add warps. It's for more efficient use of the modern GPU system. So we have this more low-level API. This is the reason why in the comparison articles, Alpaka showed better productive, but some are better productive, some are similar. So yes, let's go to the practical part of our work. First part or the practical work was adapting to the CI/CD. So we worked on the GitLab. We worked on the GitLab. We were getting more familiar with the CMake and Docker libraries. Semyon gave me 3 test tasks, but each next one was coming from the previous one, so we can start from the last test task. So we have GitLab CI YAML file. It runs in 2 stages. First stage is install requirements and runs jobgenerator.py. And jobgenerator.py, it installs all necessary libraries and runs the tests, parallelizes them. So this is how it looks on the GitLab. So after test task, our main work on the project was on the Bashi. So Bashi will be the successor to the Alpaka job matrix library generator. It provides generating of the tests, and then by the filter rules, we're filtering those some dependencies that don't work. So main part of the work on the project was writing these filtering rules and writing unit tests for them, so we can know if it works or not. And in the cases where it was not possible, we added some new functions, we modified functionality. So as the result, we also updated documentation. And if you want to check it on the GitHub, it has now a bit more cut coverage. So yes, thank you for attention. That's all project. Any questions?
Thank you, Yurii. Nice talk. Any questions for Yurii? All right, everybody. Thank you all for coming to see these talks. Thank you to the fellows and their mentors. That's all for today.